This video is a review of factoring by the method difference of two squares. So the difference of two squares occurs when you have a binomial, as in the yellow box here, where you have both first and second term as perfect squares. So if your first term is a perfect square, your second one is a perfect square, and it is a difference between the two, you can apply the difference of two squares. Essentially, if you were to square root both numbers, you would get A and B, and you would take this binomial, this difference of two squares, and it would factor down into two binomials where A and B go in both the first and second position, and then one gets a minus and one gets a plus. It doesn't matter which order you do the plus or the minus. The positive could be in the beginning, minus in the back, that's fine. For the first three examples, let's take a look. How do you recognize if you have perfect or difference of two squares? First of all, it's a difference. That's got to be there. It's not the sum of two squares. And then you need to have something squared and something squared. So is the first term in A a perfect square? Well, 16, yeah, that's a perfect square. That comes from 4. And of course, x squared would come from taking x and squaring it. So 4x squared would get you that 16x squared. So that is a perfect square. 169 is a perfect square. That's 13 squared. So 4x acts as your A. 13 acts as your B in the definition. So I have my two quantities, 4x in the first spot, 13 in the second spot. One gets a minus, one gets a plus. So that would be the factored form of 16x squared minus 169. Difference of two squares. So once again, you're looking for perfect squares. I notice the second one is a difference. What squared gives me 9x squared? Well, that would be 3x. What squared gives me 25? That would be a 5. So factor it down. 3x in both the first spots, 5 in both of the second. Minus and plus. On letter C, this is not factorable. Why is it not factorable? Well, you might think, oh, well, isn't that 11 squared? And it is. But right in the middle, we've got a plus sign. And there is no pattern for sum of two squares. It's got to be minus. So that one would be not factorable. Now let's combine a couple methods. Just because you have a difference of two squares doesn't mean we don't have, say, a GCF before we get to that spot. Always look for a GCF first. No matter what factoring you're doing, when you get to an expression, always look for a GCF and try to factor that out first. So in A here, I notice I can divide both of these by a 5. So before I go ahead and check for anything else, I want to make sure I do a GCF here. If you factor a 5 out, you get x squared minus 16. Now look at what's left over. What's left over is a difference of two squares. So now with the 5 in front, I would put x and x there because x squared is x squared. What squared gives you 16? Well, that's a 4 and a 4. One gets a minus, one gets a plus. Again, we'll do the same thing for B. It's a factor problem, so I want to make sure I check for a GCF first. I notice I can divide both of those by a 2, but I can also factor out an x. So I'm going to put 2x and then write what's left over. That would be 4x squared. And then minus, well, the whole term gets factored out for the GCF, so that'd be a 1. Now, thinking about difference of two squares here, remember, something squared minus something squared. You might glance over this and not recognize that it is difference of two squared, but it is. 4x squared comes from squaring 2x. Now 1 squared is 1. So whenever you have a 1 there, don't think, oh, there's nothing I could do with that 1. 1 is actually a perfect square. So your final answer here, with your difference of two squares factor out, would be 2x minus 1 and 2x plus 1. So there is a quick review of the difference of two squares pattern.